Thank you very much. So first of all, I thank the organizers for the invitation. It's really great to be here, and I'm enjoying staying in this wonderful place. So, I'm going to talk about something on the boundaries of Quasi Fuchsian space and some phenomena, continuous and discontinuous phenomena around that. So today, I'd like to just talk about some basic things. First of all, I'd like to define Kleinian groups. So in a Subhojoy Gupta's talk, the notion of Fuchsian group appeared. So Kleinian groups are just a generalization of the Fuchsian group. So Fuchsian groups was Fuchsian group were defined to be the discrete subgroups of PSL to R. So we just change this R to C. Then we get Kleinian groups. So this is just discrete subgroups of PSL to C. Now, so PSL to R was the group of the orientation preserving isometries of the hyperbolic plane. So that's the reason why we could identify the Teichmüller space with the space of the faithful discrete representation of pi 1 as Fuchsian groups up to conjugation. So this is this stands for the isometric group of isometries of H2 and orientation preserving, and PSL2C is equal to the orientation preserving isometries of the H3. So this is a three-dimensional hyperbolic space. So in the same way as we use Fuchsian groups as to consider the hyperbolic surface, so we can consider Kleinian groups to study the hyperbolic 3 manifold. So the PSL2R acts on the hyperbolic plane by isometry, so but it can be regarded as also as a linear fractional transformation on a circle. So in the same way, the PSL2C is linear. So it's a group of linear fractional transformations on the Riemann sphere. Okay. So you have a Riemann sphere. So it's just a one-point complication of the complex plane. And so you can consider that the action of PSL2C as like this. So if you have matrix of is A, B, C, D, then it corresponds to a linear fractional transformation like this. Where the AD minus BC is equal to 1. Now, we'd like to next generalize the notion of Fuchsian group to, well, not to Kleinian group, but there's something called Quasi Fuchsian group, which is a special kind of Kleinian groups. So now we fix a symbol S to denote a closed orientable surface of genus G greater than or equal to 2. So as in Subhojoy's talk, so we can put a hyperbolic metric there. And that corresponds to a faithful discrete representation of pi 1 of S into PSL to R. Okay, this is just a holonomy of this structure. And well, this is just a review of the Subhojoy's talk. So and so the Teichmuller space can be identified with the set of faithful discrete representations of pi 1s into PSL to R up to conjugacy. Now we are going to deform. So this can be regarded. So if you fix one hyperbolic structure, then all the other structure all the other hyperbolic structure on S can be regarded as a kind of deformation of the original structure. So there's a kind of and if you use the Fenchel-Nielsen coordinate, it's not so clear that there's a kind of deformation from one hyperbolic structure to another. But original theory of Teichmuller says there's something called quasi-conformal deformation from one hyperbolic structure to another. So if you are given a hyperbolic structure on the same surfaces, then there is something called suppose you have M and Sn, then there is a map from Sm to Sn, so preserving markings. So for any given M and N, there's a homeomorphism preserving mappings, homeomorphism, which is quasi-conformal. So quasi-conformal means something written like that. It's a partial derivative. So we are considering complex structure instead of the hyperbolic structure. So if you have a hyperbolic structure by uniformization theorem, you can identify the universal cover with H2. Then, because H2 is just the upper half plane, and it has a complex structure. And the action of PSL2R, that is a linear fractional, so it preserves the complex structure. So the hyperbolic structure naturally implies the complex structure. So if you regard them as two complex structures, then from one complex structure to the other, there's something called a quasi-conformal deformation. So this is just this one, and this is just. So if the norm, infinity norm of this ratio is less than 1, then it's called a quasi-conformal. So geometrically, it means something like this. So if you have a differentiable map, then if you look at the map from viewpoint of from an infinitesimal viewpoint, then circles around some point is mapped to ellipses. Oh, because if you consider just the differential, it's a linear map. So the linear map is affine, so it maps circle to ellipse. Okay. So then for ellipse, you can just consider the ratio with the length of the longest axis and the longer axis and the shorter axis. So this condition is equivalent to saying that this ratio is bounded essentially all over the surface. So there's some constant bounding all the ratio of this between the longer axis and the shorter axis. That's the condition written here. So such a map is called a quasi-conformal homeomorphism. And what Tachimura showed is there are always, so for any given two complex structures on the surface, there always exists a quasi-conformal map between them. And moreover, you can choose the most efficient quasi-conformal map, and it's unique. So what he showed is that the space of the most efficient quasi-conformal map from this fixed Riemann surface to another Riemann surface forms a kind of space. And it is homeomorphic to a Euclidean space of dimension 60 minus 6. And that's exactly what Tachimura defined to be the Tachimura space. So the Tachimura's definition of Tachimura space was the space of the quasi-conformal deformation starting from one Riemann surface. So the space of the marked hyperbolic structure, as in Fenchel-Nielsen coordinate, was first defined by Fricke. So originally it was called a Fricke space, but actually the Tachimura space and the Fricke space are the same thing, and they are just a difference of the viewpoints. Now, that's what the Tachimura space was. And so we now consider, that Tachimura space, so from this viewpoint, Tachimura space is a space of quasi-conformal deformation of some complex structure on the Riemann surface. Now, we'd like to now deform the structure, the Fuchsian representation, the structure of the Fuchsian representation, in the space of representation of to this regroup, PSA to C. Okay, so we fix some hyperbolic structure on that. So fix a hyperbolic structure, hypermetric M on S, and that corresponds to some as a holonomy that corresponds to a faithful discrete representation of pi 1 of S into PS to R. Now, I'd like to deform it in a PS to C. So we say faithful discrete representation of pi 1 of S into PSA2C is a quasi Fuchsian if there exists a quasi-conformal map, quasi-conformal homeomorphism F from the Riemann sphere to itself, such that for any gamma in pi 1 of S, psi of gamma is equal to the conjugation of conjugation of phi by this quasi-conformal homeomorphism. So quasi-conformal homeomorphism was defined like that. So this is the case of the Riemann surface in general, but instead of this, so we consider the sphere, the Riemann sphere, then the definition is the same, that this definition. So if, so for a given, well, so we can fix any Fuchsian representation, then what you can obtain from this by quasi-conformal deformation. So this is called a quasi-conformal deformation, or quasi-conformal conjugate, because it's a conjugate by a quasi-conformal map. What you get by this process is called a quasi-Fuchsian. So is the definition clear? So this is this is an element of the PS. So this is a linear fractional transformation on the Riemann sphere. So this is again a linear fractional. Well, it's a Fuchsian, but it can be extended to. So it's a linear fractional transformation with coefficient in R, but R is just a subfield of C. So you can regard it as a linear fractional transformation of Riemann sphere. And these two are just a homeomorphism. So if you take a conjugate in general, what you get is just a homeomorphism. But this means that after taking the conjugate, it's again a linear fractional. So if there exists such F, then psi is called a quasi-Fuchsian. So I should note that this definition doesn't depend on the choice of phi here, because of Teichmüller theory. So one, if you have two Fuchsian representations, then one is obtained from the other by some quasi-conformal deformation, like that. And you can just extend it to the Riemann sphere, and so then one Fuchsian is obtained from the other by quasi-conformal deformation. So this definition doesn't depend on the choice of phi. So that. Okay, so we know that Teichmüller space is a Euclidean space of dimension 6G minus 6. So now we consider the space of quasi-Fuchsian representations. So that quasi-Fuchsian representations of pi 1 of S modulo conjugacy. So it lies in the space of the representations of pi 1 of S into PSA to C. Modulo. So maybe modulo conjugacy. Okay. And because Fuchsian is a special case of Quasi Fuchsian, the Teichmüller space itself is contained in this space. So it's a generalization of the Teichmüller space. And actually, we know what kind of topological type it has. That's what's called the Ahlfors-Bens theory. So they show this. So there is a homeomorphism which is written as QF from the product of two Teichmüller spaces to QFS. So these two, both of them are Teichmüller space of S, but the way to give marking is different. So here is the marking is orientation preserving, here is the marking is orientation reversing. But well, in my talk, well, there's no need to distinguish these two, just regard them as the product of two Teichmüller spaces of S. So in particular, it is homeomorphic to the Euclidean space of dimension 12G minus 12. So let me show you briefly how Ahlfors and Bens proved this. So you start from some Fuchsian representation phi. So Fuchsian representation is a linear fractional representation with entries in R. So it acts on R hat instead of the C hat. But you can extend it as an action of the C hat because R is just a subset of C. So it acts on Riemann sphere, but it preserves real axis. It stabilizes the R axis, so the real axis. Okay. It acts like that. So, and you can see if well, it also preserves this left hemisphere and the right hemisphere. Okay. Left is mapped to the left, and the right is mapped to the right. And if you just consider, so phi was the Fuchsian. And so you have here, this is the right hemisphere, this is the left hemisphere. Okay. And if you consider the quotient of the right hemisphere by image of pi 1 of S, that's the Fuchsian group, then what you get is isometric, well, or conformal to the original hyperbolic metric. So this right hemisphere can be identified with H2. So H2 lies here. So this is the Poincaré model of the hyperbolic plane, and its circle at infinity is the 1-point compactification of R. So hyperbolic plane lies there, and you can identify the right hemisphere with the hyperbolic plane by just considering the projection. then this is, well, so if you identify this with H2, then taking the quotient, what you get is just isometric to the original hyperbolic method. So this Fuchsian representation corresponds to the hyperbolic structure on S, which I wrote by M. Okay. And at the same time, if you consider the left one, then again you have the same hyperbolic surface. But well, here there's a difference of the orientation. So if you put the orientation coming from the ball, then for this the orientation is preserved, but for this the orientation is kind of the reverse. But well, if you just ignore that, then you get the two isometric hyperbolic surfaces. Now, you consider the quasi-conformal deformation of this one. So, well, Taichi-Miura's theory says if you give something called Beltrami differential, that is this is just this one. So from quasi-conformal map, if you consider that the quotient like that, then it's called a Beltrami differential. If it's quasi-conformal. So but the other way around is also true. That means if you give some differential on a Riemann surface, well, the differential is meaningless if you just consider quotient. So maybe if you give a function, complex valued function on a Riemann surface with infinity norm less than 1, if you give something like that with norm less than 1, then you can solve the equation like this and get the solution F. So if you give something called a Beltrami differential, it's just a function in a setting, then you can get something called you can get, this is if you solve this kind of equation, this kind of partial differential equation, then you get the quasi-conformal map. That's Taichi-Miura's, that's the part of the Taichi-Miura theory. So, to deform the complex structure, what you have to do is just give a Beltrami differential. So it's possible to deform this side and that side by different Beltrami differentials. So you give mu and probably mu plus and mu minus. So you give two different ones. Well, and then if you solve the equation like that on this side using mu plus, and on that side using mu minus, then you get something F. So the solution, and put 0 on the real axis. Then you can solve the equation on the entire Riemann sphere. Now what you get is something like that. So it's just a quasi-conformal map such that this quotient is mu plus in omega plus, and this is mu minus in omega minus. Okay. And here, so you have a new image of, so this is image of omega plus by f. Then you have here the image of the omega minus. And if you consider the quotient, and at the same time, I didn't say anything about about the differential and automorphic form, but you can put mu plus, which gives the quasi-conformal deformation of the Riemann surface here, and the quasi-conformal deformation of the Riemann surface here. So it's compatible with the action of pi 1 of s. So what you get is something like that, and psi, there is a kind of the automorphism from the action of a Fuchsian group to some action. So I mean, if we define the psi of gamma to be this one, then well, if you give Beltrami differentials to give conformal structures, new conformal structure on this Riemann surface and that Riemann surface, then what you get is quasi Fuchsian representation. So this becomes quasi Fuchsian. So it might be difficult to understand the situation, but let me just put it this way. So you start from Fuchsian representation. So for Fuchsian representation, you have two Riemann surfaces. And they are isometric, or they are conformal. So if you regard it as hyperbolic surfaces, these two hyperbolic surfaces are isometric. What you get from here and there are isometric because we can identify this to the hyperbolic plane there, and you can identify this side there, and the action is compatible with this identification. So they are the same Riemann surfaces. So after the deformation, so we just consider two deformations. So one, on the right-hand side, you deform it to another. So from SM, you consider another hyperbolic structure, N plus. So that's another point in the time space. And from here, you consider another point in the time space. So we have 2 points in the time space. Then corresponding to that, you get the quasi-conformal deformation like that. So if you put the deformation from the M to N plus on the right hemisphere, and the deformation from M to N minus on the left hemisphere, then you get the entire deformation, which is deformation to quasi-Fuchsian group. So that's the way they define this parametrization. So this is called simultaneous uniformization. Now, so we know that there's a generalization of Teichmüller space, which is called a quasi-Fuchsian space. But we can consider bigger space in a representation space, which is just general faithful discrete representations of pi 1 of S into PSL2C modular conjugacy. Because Quasi Fuchsian representation is also faithful discrete representation of pi 1 of S into PSL2C. So Quasi Fuchsian space is a subset of this space, or subspace of this space. So again, this is regarded as a subset of a faithful discrete, or this is regarded as we just drop the condition of faithfulness and the discreteness. Just consider the representation space in modular conjugacy, then this is just a subset of that one. And you can put the topology there as a topology induced from this representation space. So AH of S is also some topological space, and QFS is a subspace of that space. Okay. So in general, well, not in general, the fact is that AH of S is really larger than QF of S. So that's first proved by Bears. So the complement of Q is so QF of S in AH of S. So actually he constructed something called B group. B stands for boundary, not Bears. But then he defined something called B group, and so that's not contained in QF of S, but it's contained in AH of S. So and now we know. So this is theorem. What's called the density theorem. So in this version, it's proved by Minsky and Minsky, Bromberg, and Bromberg. So there's general density theorem for general Kleinian groups. That's the proved by the Namaji Sot and myself. So, but in this setting, these three people proved that. So density theorem said that AHS is a closure of QF of S. So therefore, we can understand the entire space of faithful discrete representation. So if you just look at the definition, then this seems to be a real generalization of Teichmüller space, because Teichmüller space was a faithful discrete representation into PSL2R. So we just change that PSL2R to PSL2C, then we get that space. So this seems to be a real generalization of Teichmüller space. But the Quasi Fuchsian space is a kind of the analytic generalization of the Teichmüller space. The analytic generalization of Teichmüller space is a proper subset of the real generalization of Teichmüller space. But it's just a closure. So that's what we are saying here. And what's difficult to understand? So it seems to me, maybe someone thinks that then if it known that it's just a closure, then it's simple. So you just putting boundary to so we know this is a Euclidean space. So by putting boundary to Euclidean space, so you can get the H of S. But it's not the case. The way to put the boundary to QFS is very complex, very complicated, and it's very difficult to understand the entire deformation space. Actually, we don't have the complete picture of AH or AH of S. This is a very complicated kind of space. Actually, it's not a manifold in the topological sense, so it's not a topological manifold. And, so it has singularities. And there are many things happening on the boundary of pi 1 of S into PSS to C modulo conjugacy. So, well, it's sometimes called the character variety of the pi 1 of S. So, what we are going to say next is in a short like this. So that in QFS, geometry and what should I say? Is the algebra are the same. Well, or I will explain what they mean. But in AHS minus QFS, they differ. So let me define something called the geometric topology of Kleinian groups. So it's a space of Kleinian groups. So this is something called geometric convergence. So suppose you have a sequence, GI is Kleinian groups. So suppose you have a sequence of Kleinian groups, GI, then GI is said to converge to another Kleinian group geometrically if two conditions as follows hold. The condition is this. So for any element gamma in capital gamma, there exists an element GI contained in a capital GI such that gamma is a limit of GI. So any element here is a limit of some element, sequence of elements, which is contained in GI. So that's the first condition. And the second condition is that if you have a subsequence GI sub J of GI and pick up the element gamma, probably it's better to write it Gij from Gij, then assume Gij converges in a PS to C, then its limit is contained in gamma. So any convergent element taken from the subsequence should have limit in gamma. That's the second condition. Then the gamma is said to be, then this convergence GI to gamma is set to geometric convergence, and the GI is set to converge geometrically to gamma. Gij is a subsequence of. So for any subsequence Gij, such and any element Gij in the Gij, which has a limit in PS to C, its limit lies in gamma. So there's any subsequence and any. So this definition may look strange, but it has a more geometric meaning. So you just consider quotient of hyperbolic space by GI. So you get some hyperbolic three manifold. Then we fix some base point in the hyperbolic space, and you just project it down here. This is a projection. Then this pair converges to this is again the projection of this point in the sense of Gromov. The Gromov convergence is something like this. So if you have E for any R, so there exists K I and Quasi isometry between R ball, probably it's better to write like R ball centered at the Xi to the R ball centered at Y. So there is a Quasi isometry between them. Well, Ki Quasi isometry such that Ki, well, maybe Ki by Lipschitz. So that should be better. By Lipschitz diffeomorphism such that Ki goes to 1 as I goes to infinity. For any fixed R, you can take a Quasi isometry between the two balls. So one in H3 over GI and the other in H3 over gamma. And so it's by Lipschitz, and it tends to isometry as I goes to infinity. So that's the Gromov convergence. This is the definition of Gromov. Probably someone call it a pointed Gromov convergence because we specify the base point. So these two conditions are equivalent to this condition. So if you just have that, then H3 over GI converge in the sense of Gromov to H3 over gamma. So this means the quotient of hyperbolic three manifold looks like quotient of the hyperbolic manifold by gamma. So quotient of the hyperbolic three space by GI looks like quotient of the hyperbolic space by gamma more and more as I goes to infinity. If you look at them focusing on the bed point Xi and Y. So here I said QFS, in the QFS and geometry and algebra are the same thing. That means if you have a convergence in QFS, so if phi I is in the QFS, and phi I converges to psi again in the QFS, then phi 1 of, so this is a Quasi Fuchsian group, converges, again this is a Quasi Fuchsian group, also geometrically. So this convergence is a convergence as representations, so it's an algebra because it's a convergence of the representation. So you just pick up the generator system and as an element of the PSA to see each matrix corresponded to a generator converged to that one. So that's algebra. But here you have a geometry like that. So algebraic, so this is called algebraic convergence. So algebraic convergence implies geometric convergence inside QFS. So this is easy to prove. I'm not going to go into details here, but what I'd like to emphasize is this is not true in the complement of QFS. But there exists psi in AHS minus QF of S, and phi I contained in QFS converging to psi, such that phi I and pi 1 S does not converge to psi of pi 1 of S geometrically. Okay. So now, let us review this definition. So well, here we don't assume GI is the image of some representations, but suppose GI is the image of the representation phi I of pi 1s. So let's suppose, well, in the definition, suppose GI is phi 1 of pi 1s, and suppose phi 1 converges to psi. Then look at this condition. So the GI itself is a subsequence of GI. So you just consider phi I. So fix some element in the pi 1 of S, C, and consider phi I of C. That's in the phi I of pi 1 of S. So as a gamma, as a Gij, you can just consider phi sub IC. And the phi I sub C converges to psi C. So it has a limit in the PSA to C. So that must be contained in the geometric limit. So that means for any C in the pi 1 of S, psi C must be contained in the geometric limit. If you have a geometric limit of this sequence, suppose GI converges geometrically to gamma. Well, in general, there's a compactness of the Gromov convergence, which says that if you take a subsequence, you always have a geometric limit. So so after passing to a subsequence, you have a geometric limit gamma, and this gamma must contain all phi of C. So that means phi, oh, no, not phi, psi of C. So psi of pi 1s should be contained in a geometric limit. So that's always true. So, but in that case, it's not just the inclusion, but it's the coincidence or the identity between two. But here, I'm claiming that there is a case when this is a proper inclusion. So let me just show you what kind of example we have. So the sequence is concretely constructed like this. So I use the symbol C there. Maybe so I should use sigma instead. So this is surface S. So I'm considering the case of the genus too, but well, any surface, any closed surface will do. So just pick up some essential simple closed curve sigma on S, like this. And then consider something called a then twist. Then twist. So you have a hyperbolic structure here. So realize sigma as a closed geodesic in with respect to the hyperbolic structure M. So cut this surface along sigma, like that. So then after rotating one of them by 2 pi, you paste them up again. So if you have a curve like that, then what you get is a curve like this on this surface. So after rotating by 360 degrees, you just paste them up. Then you get the new hyperbolic surface. This hyperbolic surface is isometric to the original one, but the marking is different. The natural marking given here twist around, go around along this sigma. So if you put the marking, the original marking was mapped like that. So, but the marking, the real marking is like that. So the marking here, if you just consider marking here, then it's different from the one given from that. So that it's just a change of marking, but so in the, they are isometric. So in the modular space, they are the same point, but in the Teichmüller space, they are different. So now we consider a sequence of the Quasi Fuchsian representations obtained by then twist, iteration of then twist. So you consider, and from SM you get by then twist you get something like that. So this is written as tau c, no, not c, sigma, tau sigma of M. Okay? This is again a point in the Teichmüller space. So you consider sequence like this. So for any natural number n, you consider the something like that. So it's Ts times Ts bar. Well, maybe I can put bar, yeah, but just identify Teichmüller space, the second Teichmüller space with the first one. Okay. You consider that such a sequence. So then put QF. Then you get the sequence in a Quasi Fuchsian space. Okay. In a AH of S, well, we can actually Baird proved that such a sequence must converge to some Kleinian group, or which is called the B group. And it's well, I haven't defined it yet, but it's something called geometrical finite B group. So I have 8 minutes left. So maybe let me define what the meaning of the geometric finiteness. So so we are considering let G be a Kleinian group, and consider the corresponding hyperbolic manifold H3 over G, so something like that. And then you can define the convex core of that space, that manifold, which is smallest convex submanifold C in H3 over G that is deformation retract of H3 over G. So convex submanifold So if you have two convex manifolds with this property, then their intersection is also has the same property. So you have that smallest one. So for instance, the case of the Fuchsian group, the convex core is just a totally geodesic surface coming from the Fuchsian representation. So in general, for general Quasi Fuchsian group, it's something bigger than totally geodesic one, but still it is compact. So if the convex core has finite volume, then G is said to be geometrically finite. So Quasi Fuchsian groups are a typical example of the geometrically finite groups. But even outside Quasi Fuchsian space, there are infinitely many geometrically finite groups, which are called a geometrically finite B group, for instance. So it's something like this. So you have a so you started from some Fuchsian, and as a limit, you get something like this. There is something called cusp corresponding to curve sigma, and here you have a compact surface homeomorphic to S. And this is a picture of the convex core. So it has finite volume, but it has something called cusp. So cusp corresponds to a parabolic element. So it corresponds to something like parabolic. So sigma is taken to a matrix conjugate to that. So that's the algebraic limit. So this is psi in this case. But for this sequence, geometric limit is larger. Actually, geometric limit is not isomorphic to a surface group. So gamma geometric limit of the pi 1, pi 1. Yes. It has a form like this. So you have, so it's again a geometrically finite. This is again a geometrically finite. So as a manifold, it's homeomorphic to the manifold obtained from the trivial interval boundary over S with a neighborhood of the, so this is S cross 0, 1 interval with sigma cross a half deleted. So it's a complement of sigma times half in the inside. So it's a convex core is homeomorphic to that. And algebraic limit is obtained from so algebraic limit is in general is a subgroup of geometric limit. So this picture is obtained from this by taking a covering associated to the lower surface. So you have something. So you have something called. So this corresponds to again the parabolic elements, parabolic group. So there is a parabolic group of the rank 2. So if you have a parabolic element like that, then you can consider another parabolic element like that, such that the one and that one is linearly independent. Then you can get a discrete subgroup of the PS2R, which is isomorphic to the abelian group of rank 2. So this here you have such a group. So of course the surface group doesn't contain an abelian group of rank 2. Okay. So my watch is different from that. So how much time? Oh yeah, so this is not correct. Okay, right. I still have 7 minutes or something. Okay, so here you have a abelian subgroup of rank 2, but the surface group doesn't contain abelian group of rank 2. So this is evidently is different from the surface group. It's larger than that. So such an example appears in a limit, in an algebraic limit. Well, if you consider geometric limit corresponding to the sequence converging algebraically outside the Quasi Fuchsian space. So, but still, you have some continuity of some kind of invariant even to the even in the entire AHOS. For instance, well, I'm not sure if I have enough time to explain this, but just let me state the theorem. So this is originally due to Thurston, and but he hasn't written up it in details, and Broach published and the detailed proof on and generalized it also. Okay. So we consider something called the length function from the space of the faithful discrete representations, and something called the measured lamination space. I will explain what it is. And in something, which is completion of the space of simple curves on S. And then if you define the length function like that, then so for this means for representation psi and measured lamination lambda, L phi lambda is the length of the realization of lambda, probably psi lambda in H3 over psi pi 1 over S. So I will explain what it means. So measured lamination space, I'm not going to define it precisely, but it's a kind of the completion of the space of reciprocal curves. So let me just explain what it is in the case when the measured lamination is a simple closed curve. So you have some simple closed curve C on S, so it's a simple closed curve. Then L psi C is the length of the closed geodesic homotopic to psi C, psi of C in H3 over psi pi 1 over S. So for each C, you can consider the closed geodesic in H3 over psi pi 1 over S, realizing the homotopic class psi C, then it has a length. So if it's parabolic element, if it happens to be psi C happen to be parabolic, then we define its length to be 0. Otherwise, it's realized as some closed geodesic, and its length is L psi C. And MLS is the completion of the space of simple closed curve And so you have something called the measure elimination, which is a generalization of simple closed curve. And also for measure elimination, we can consider its realization as geodesic, and you can define its length. And this is the function giving us its length. And what proved there, what's stating this theorem is that this function is a function of two variables is continuous, even though the AHS doesn't, in general, AHS doesn't respond respond well with respect to geometric topology. So maybe in the beginning of the second one, I will explain what it's true. So I should stop here for today. Thank you very much.